We have 13 questions to do for today on page 569. We're going to go over several of those today, including 3, 4, 8, 9, 10, 12, and 13. Starting with number 3. It says, describe the difference between the electric potential and electric potential energy. Remember the analogy that I gave you yesterday? We talked about U being like charge. Okay, you are a coulomb of charge. You are a coulomb of charge. You are a coulomb of charge. And you are a coulomb of charge. Okay, we're all a single coulomb of charge. Your arms are like energy. There's 30 of us in this room right now. How much energy do we have? 60. Okay, that's energy. How much potential do we have? Potential is like arms per person or energy per coulomb of charge. What's our potential if we have 60 joules in this room of 30 coulombs? How much? Yeah, it's 2. 2 coulombs, or sorry, 2 joules per coulomb, or we'd say 2 volts. 2 joules per coulomb, 2 arms per person, 2 volts. So energy is the whole, and potential is the energy, the whole energy, by the number of coulombs you have, or per coulomb that we have. Does that make sense? Energy and energy per coulomb. 4, at a point in Earth's atmosphere, the electric field is 150 newtons per coulomb downward, and the gravitational field is 9.8 newtons per coulomb downward. Let's draw both of those. This is my electric field downward, and it's 150 newtons per coulomb. This is my gravitational field downward, and it's 9.80 newtons per coulomb downward. We have a proton placed in there. We have a proton in there. Which way is the electric force on that proton? Which way does it act, upwards or downwards? Downwards, are you sure? Are you sure? You're positive. She's positive because the force is always with the field. I'm positive the force is with the field, right? The electric force is downwards. And what about the gravitational force here? Gravitational force, of course, is going to be downwards, right? It's always downwards, pointing towards the Earth. So we'll say Fg is downwards. Now, we're not actually asked to find the net force here. We're just asked to find the individual forces. But if we were asked to find the net force, that'd be okay. We'd solve for each one of them and then add them up, both as negative answers. I'll solve for them individually, though. A is the electric force. We have an experiencer in that electric field. And we're going to use the equation E is equal to F over Q to solve for that. Just rearrange to solve for F. I get Q times E. Q is 1.6 times 10 to the minus 19. And the electric field strength is 150. And I think when I do the math there, it works out to be 4.0, I want to say, times 10 to the minus 17. Is that right? Somebody double check that. No. No, that's not going to be it. 2.4 times 10 to the negative 17. And of course, we established already that it's a downward force. It asks us not to determine the magnitude. It asks us to determine the force. So we do need the direction, which includes the fact that it's downward. Okay, the gravitational force on the proton at this point. To find the gravitational force on the proton, we're just going to say F is equal to m times g, right? The mass times the gravitational field. So it's, what, 1.67 times 10 to the minus 27 kilograms times 9.80. Usually it's 9.81. It's okay. 1.67 times 10 to the minus 27 times 9.8 gives me a value of 1.63 or 1.64 times 10 to the minus 26. Do you guys remember at the beginning of the unit we talked about electric force and gravitational force? And we said one of them was bigger usually. Which one did we say was bigger? The electric force is normally bigger. And sure enough, in this case, the electric force is bigger. By quite a bit, right? About 1 billion times bigger, 10 to the 9 times bigger. Next question we want to go over is question number 8. It says a 2 kilogram charge jumps across a spark gap in a spark plug across which the potential difference is 1,000 volts. How much energy is gained by the charge? How much energy is gained by the charge? You could use what we did yesterday to solve this, actually. EI is equal to EF, but we don't actually have to. You could, but you don't have to. Remember that earlier today and yesterday, we defined potential as the energy per coulomb. Potential, big V, is equal to energy per coulomb. There is an equation on our data sheet that's not quite like this, but that will certainly remind us of this. It says on our data sheet, change in potential or potential difference is equal to change in energy over charge. So this one's on your data sheet, this one's not. Okay? In the end, they both work the same way. We're looking for the energy gained, so we're actually looking for this, delta E. We're going to say delta E is equal to Q times V. Remember yesterday, we said QV, but in those problems, except that yesterday we weren't looking for the energy gained, we were looking for just the energy at one spot, hence QV. If we're looking for the energy gained, it's Q times delta V. And of course, this is the version that appears on your data sheet. My charge is 2 coulombs. My potential difference here is 1,000. So we're going to say the change in energy is 2.00 times 10 to the 3. And what would the units be? Joules. It'd be joules. We've got, this is coulombs, 2 coulombs, and potential difference is either volts or potential difference could be joules per coulomb. Cancel with the coulombs and we end up with joules.
Is it still right if you say volt coulombs?
It would be, yeah, that would be a different set of units that we don't usually see, but that would be correct, yeah. Having said that, you're probably not going to see volt coulombs as one of the options, as an ABCD option, right? But it's correct, yeah. Number 9, determine the magnitude and direction of the field at point P as shown in the diagram. So let's see here. We've got we've got a field caused by the 50 microcoulomb charge that's to the right. We've got a field caused by the blue one here, the 10 microcoulomb charge to the left. Away from the positive, toward the negative. Away from the positive, toward the negative. So we calculate both of these fields now. We're going to say E1 is equal to KQ over R squared. Q is 50 times 10 to the minus 6 coulombs, divided by, what distance are we going to use there? 0.45, right. We don't want to go 0.3 here. We don't want to go 0.15. We need the total distance from that charge to the point, which is 0.45. And then, of course, we've got to remember to square that. So we say 8.99 times 10 to the 9 times 50 times 10 to the minus 6, divided by 0.45 squared, and we end up getting 2219753. Newtons per coulomb. What's the other set of units that we could use there? Volts per meter, of newtons per coulomb, volts per meter. Now we calculate the second one. KQ over R squared again. Q is 10 times 10 to the minus 6, divided by 0.15 squared. $399.5555. And then what do we do with those two numbers? Add them up. But we have to be careful to make the blue one negative there, right? Somebody was asking me before class, question real similar to this actually. Why do we not use KQ1, Q2 over R squared? Like there's two charges here. Wouldn't it make sense, instead of doing it in two separate steps like this, wouldn't it make sense to use F is equal to KQ1, Q2 over R squared there? Matt, are you saying no? It wouldn't make sense? How come? Good. I mean, that's a correct, valid equation to use, but understand that if you do use that, you're not getting what you're looking for. You're getting something else. So if you use that, you will get the correct force between those two charges. But that has little or nothing to do with the electric field at point P due to those two charges. When you're calculating an electric field, you gotta always just do one at a time. Number 10. A uniform field exists between two oppositely charged parallel plates connected to a 12-volt battery. They're separated by this distance. What's the magnitude of the electric field? This is a uniform or a non-uniform field? Uniform, yeah. So it means we use the uniform producer equation, which is, yep, E is equal to delta V over delta D. This is relatively straightforward. Question A is, we say 12 volts divided by 6 times 10 to the minus 4 meters, which gives me 2.00 times 10 to the 4. That would be, what units do you want to use there? Shirley, what units do you want to use there? You can say volts per meter, sure. Or what's the other set of units you could use there, Kathleen? Newtons per coulomb. Either one works there. Usually volts per meter is probably the one we'd use there because of the equation, though. And B, oh, this is a similar question that we had from that other one. If this charge moves from one plate to the other, calculate the change in electric potential energy. So we're going to say, once again, delta V is equal to delta E over Q, which is that equation we saw yesterday. Delta E is equal to Q times V. So the charge here is, we drop the sign of the charge. We always do when we plug it into an equation. Times the potential difference times 12 there. So multiply those two numbers together, whatever we get there. Delta E in this equation, by the way, stands for change in electric potential energy. But, technically that is. But remember that if potential energy gains a certain value, then kinetic energy will lose a certain value, the same value, right? So even though technically we talk about change in potential energy there, technically it could be change in kinetic energy as well. And the last two questions, a little bit more qualitative in nature. Number 12, I love this question. Explain why only one of the electroscopes connected to the hollow conductive sphere in the illustration indicates the presence of charge. First of all, which one does indicate the presence of charge? The first one or the second one? First one. And how do you know that? The leaves are separated. That doesn't tell us whether it's positive or negative, right? It just tells us that we have charge present. Now, why is that one indicating the presence of charge and the second one is not, despite the fact that they're both connected to the same thing, which is charged negatively?
Charges go to the outside of the object to the surface.
Yep.
That one's connected to the surface.
To the inner surface. Yeah, good, good. So this one's connected to the outside, this one's connected to the inside, and electric charges, that is excess electric charges, that will cause an electroscope to have a reading, always go to the outer surface of the conductor, which is exactly what's happening right here, right? The electrons go here, okay, the electrons go here. This guy isn't going to be touching them, so it's not going to be reading anything. And finally, number 13 says 2 points at different positions in an electric field have the same electric potential. Would any work be required to move a charge from one point to another? They have the same electric potential. They have the same energy per coulomb of charge. Do you have to do any work to go from this spot that has a certain value of coulombs per charge, joules per coulomb, to this spot with the same number of joules per coulomb? What's the answer? Who says no? Who says yes? All right. So that was not unanimous. Well, of the people that voted, of the two people that voted, it was unanimous. There's where democracy falls apart on us because those two people were wrong. You would not have to do any work on it to move it from one spot to another spot with equal potentials. Okay? Potential is energy per coulomb. If you're going from one spot with this, say, 5 joules per coulomb to another spot with 5 joules per coulomb, your difference in energy per coulomb is 0. And if your difference in energy per coulomb is 0, then your difference in energy would be 0. And work is defined as the change in energy. So you wouldn't have to do work there. The answer is no. I'm going to draw a picture here, though. And I want to expand upon that one a little bit. That's a great question, and I think there's some value in expanding on that question, okay? Let's put a positive charge right here. Positive charge right here. Now let's label 3 positions, 1, 2, and 3. Would any work be required to move that charge to position 1? Brennan? No. No, it wouldn't. Here's another way to think of it. In Physics 20, you learned that work is equal to force times displacement. Do you remember that? What was special about force and displacement in this equation? What allowed us, remember it was actually equal to force times displacement times cosine theta, remember that? It's a cos theta on the end of it. What's special about this equation when I drop the cos theta? If I just write it as F times D, what has to be the relationship between F and D? So they have to be on the same plane. Yeah. So they have to be parallel to each other. F can be in the same direction as displacement or opposite direction to displacement, but they got to be parallel. If they're not parallel, then we've got to use FD cos theta to essentially find a parallel component of the force. Right? So F and D have got to be parallel to each other here. Which way is the force acting on this positive particle in this situation? Downwards. Which way is the displacement? If we're going to position 1. It's to the right. The displacement's to the right. Is that force and displacement parallel to each other? No. So there wouldn't be any work required to move it from this position to position 1. Make sense? Let's make a little table here. What about position 2? Would you have to do work to move this positive charge from this position, the original position, to position 2? Yes, you would. And you would because the force acting downward is parallel to the displacement that is upwards, right? So you would have to do work in order to go from the original position to position 2. What about to go from the original position to position 3? Yes? How would that work compare to the work done to get it to position 2? We'll call this one W2, however much work that is, right? Force, whatever that force is times the displacement. Okay, how would W3 compare to the work done to get it to position 2? Would it be more, less, the same? Say the same, Matt? Why would you say it's the same?
Because the y components are the same distance.
Yes, the y components are the same displacement, and the x component doesn't matter because there is no x work, right? So we would say that the work done to get it to position 3 would be exactly equal to the work done to get it to position 2. If you ever see a problem like that that talks about the work done or the change in energy to go diagonally like this, all that we care about is the part that's parallel to the electric field. Does that make sense? Not the part that's perpendicular to the field, only the component that's parallel to the field. Okay, that's kind of like remember the FD cos theta. Okay, if you looked at this angle right here, and you said force times displacement times cosine theta, then you would end up with essentially the y component of that. And you would end up with the work going to 3 being exactly the same as the work going to 2. Okay? Good? All right.